Hey there. Okay, so we're going to talk about a couple of data conditioning techniques because, as we know, if you have good data going into your algorithms and assessments and evaluations, then typically you get good data coming out, or at least better results, more reliable results. And so, two of the methods I want to mention today and talk about are structurally oriented filtering, or SOF, and also spectral balancing. Okay, so let me mention first that both of those methods are ones that are often available in software packages, so you can usually apply them after processing but before interpretation. So if you notice things after you do your quality control check through your seismic data, you can look and see if you could apply these techniques. So starting with structurally oriented filtering, this is one way that we can slightly clean up the seismic images. And so it's kind of a way to get out some of that extra noise. And so here's an example of what some raw data looks like. And you can see that there's some small scale noise, kind of up here, and just some fuzziness throughout the image. And so after applying structurally oriented filtering, this is what the data looks like. So I'm going to go back and forth a few times. Original data, SOF. Original data, SOF. And you can notice some smaller scale, higher frequency horizons that are a little bit more clear to see. So now that I've pointed those out, let me just go back one more time. And you can kind of just see how those improve just a little bit. And so one other thing, whenever we go to remove noise or do any type of data removal, it's best to look and see at what is missing now. So what did you take out? And so this is an example of the rejected noise from that vertical section that I just showed you. And so we can notice that there's some data that's been removed. Like it has a little bit of structure to it, geologic structure to it, but not too much. So we can feel safe that we didn't remove anything that we may need to interpret later on. So structure-oriented filtering, at least in the ASPE software, the software that my research group uses, it has kind of a 3-step simplified process. And so the first step that you have to do is you have to calculate dip of the geologic layers. And so there's a lot of ways to calculate dip, and I talked about this in the geometric attribute lecture. But the reason you want to calculate dip is because when you're looking to compare the waveforms next to each other, you want to make sure that you're doing it along dip. The second step that you want to do is you want to calculate some sort of coherence. So this could be similarity, this could be variance, what are some of the other ones, but any type of coherence. And so you do this because you want the algorithm, the SOF algorithm, to know where there's discontinuities. Okay, and so similarity shows us discontinuities because you don't want to remove or identify noise that's moving from one side of a fault to another, or from outside of a channel to inside a channel. And so you can use these similarity cubes in order to tell the filter, hey, back off a little bit right in this area. Okay, and so this is kind of a way to do, to set you up in order to do some smart filtering. And so you could think about it this way, that you want to be able to use a higher filter, so like kind of adaptive filtering. You want to be able to filter a little bit more in areas where you know that everything is fairly similar to each other. Okay, so you could remove that speckly noise, that random noise in areas where the data should be similar. And then as you get lower coherence, so there's more dissimilarities, maybe you're approaching a fault, or you have a very I don't know, what would be a good one? Like a turbidite, like you have a higher coherence in a turbidite. And so you don't want to overfilter there because you wouldn't expect it to be smooth. And so in the ASPE algorithms that we use Kuwahara windows. And so this is a very adaptive window that allows you to kind of select an area. And of course, most software algorithms, if you're using them, you should be able to fiddle around with them a little bit, but it allows for an adaptive filtering. And so the way it works is that you have different windows around your target, so around the area you're trying to look, and you have these overlapping windows. And typically we use somewhere between 9 and 13 overlapping windows. But the algorithm will look at these windows, they'll see which window has the highest similarity and the lowest variance, and then choose that window for filtering, so around that area. So as you get closer, like let's say we have a fault over here, okay? So you would want to choose one of the windows that's over to the left of the fault rather than choose one of the windows that encompasses the fault. And so that's the way it's working. So let's look at it with some real world data because that's fun. Here's an example where we haven't, so we're looking at the Gulf of Mexico. This is like the 1990s vintage data just offshore. And we've got a lot of cool features in here, whether we look at it in the inline on the left or the cross line on the right-hand side. You can see some faults in both the inline and the cross line. So some nice listric faults. There's some small scale channels. So I'm trying to pick out a few of those, particularly in the shallow part. And there's even a couple of bright spots that might be of interest to us, like abutting up against some of the faults. And there's also some footprint in the inline direction. And you can see a little bit of that up here. So you see I got some footprint up there. Okay, so what we want to do is apply the SOF. And so this time I'm doing it without any of that edge preservation, so without the Kuwahara filter. And when we look at the noise that's removed without the edge preservation, we can see that it's removed some of the footprint. It looks like it's removed some of the information from the faults. Like you can particularly see it over here in this cross line because it's used a window that went across the fault. And so we ideally don't want that to happen. So now we could look at the data when we use the Kuwahara filter, and then also the noise that's removed from it. And so we have a little bit more random noise here, and a little bit less of the geologic noise is removed. It definitely looks a little bit more random. And so let me just go back and forth. So here's the noise with the Kuwahara filter and the noise without it. And if you look up here, you could definitely see how less of that geologic noise is going to be removed with the Kuwahara filter. So without edge preservation, and then with some edge preservation. Okay, all of this is really important because the cleaner, the better our amplitude data is, then the better our seismic attributes are going to look after we run them through our algorithms. And so here's an example of energy ratio similarity. So one of my favorite types of coherence. We're looking at two different time slices at 0.8 seconds and then down at 2 seconds. And we've got some channels in here. We've got some faults. And so we're looking at it now without SOF applied and then with SOF applied. And so you can see they're much clearer. They're much cleaner. The thing that just popped into my mind is it would be much easier to map the fault networks. And if we were going to use this ERS volume in order to do some, CNN fault detection, we would definitely want to have a cleaner version to start with. Okay, so the second method I wanted to talk about is spectral balancing. And so this is a method where we can try to improve and up some of those higher frequencies if we need them in order to do structural or stratigraphic interpretation. Okay, and so what we want to do here is, and keep in mind when I was talking about amplitude anomalies, that this isn't necessarily something we want to apply when we're looking at AVO or other amplitude effects because we're artificially boosting the amplitude. But it's good to do for structural and stratigraphic and understanding the system in general. So here's one example of the original seismic amplitude. This is some onshore data down in Texas. So we've got without anything applied, just the original data. We've got a couple of formations of interest up here, some karsting and collapsing features. And after we apply spectral balancing and we improve those higher frequencies, you can notice that we've got an increase of frequency content in the target interval. So I'll go back and forth from the original data to the spectrally balanced data. Okay, here's another example This one is offshore New Zealand. So here I've kind of highlighted in these colored squares different areas for you to pay attention to. So here's our original data and then our spectrally balanced data. And so you can notice how it kind of upped some of the amplitudes, making some of those higher frequency events easier to interpret. So original, higher frequency. And the way this works is that we can suppress, so we look at different filter banks when we do the spectral balancing. So we don't look at all of the frequencies at once. It's kind of easier to show in pictures, so I'm gonna show you in a minute. But it suppresses some of that noise that we end up getting in the low frequencies compared to the higher frequencies. And so here's an example of our original data. Here's an example if we spectrally balance just like 5 to 120 hertz, so kind of ignoring maybe the highest noisier ones and then the lowest ones. And what you'll notice here is we get a lot of those kind of very steeply dipping noise trains in here. And so that's not ideal. And so that's why we want to include those lower frequencies and filter them out pretty well. And so here's what it would look like after we do the low frequency structurally oriented filtering. Let me go back and forth between those for a minute. So the original, and then after the low frequency structurally oriented filtering. So it's happening kind of helping out with the low frequencies and then also the high frequencies. And so this is what it ends up looking like. So as we get, if you look at the time variant spectra, so as we go deeper, so we've got time on the vertical axis, with our original data, you can see that most of our frequencies are between about 10 and maybe 50, 60 hertz. But after we do the low frequency SOF and the spectral balancing, what we've got going on here is we've extended those frequencies out. We've also filled in some of the deeper part. And so one of the things I forgot to mention is that we use SOF for those low frequencies. So that's why we call it the low frequency SOF. Sorry about that. Okay, so just some key concepts to summarize is, like the overall thought I want to put in your head is that there are some post-processing workflows that we can do when we are handed the data as interpreters and we want to clean it up a little bit. Some of the things, these are two of the easiest ones to do that I think a lot of software packages do have available. We want to try to reduce the noise in order that when we run algorithms with attributes or with machine learning, we're running them without as much noise as there could be. And then the other key thing is to always look at the noise that you're removing, because that's really important to make sure that you're not removing anything that has a geologic signal or a geologic source that you're interested. So as always, thank you very much for listening.